Dear students, today we will find the potential energy due to a system of charges. Previously you have found the potential energy of a charge inside an electric field. That already you have calculated. Now we will find out the potential energy of a system of charges. So you know potential energy is the energy due to position or configuration in a field of force. Already you know that. Now we are discussing the electrostatic potential energy. That means the energy due to the position in an electric field. And what is the potential energy due to a system of charges? Suppose there is a system of charges, the potential energy, how it is calculated? It is calculated by calculating the work done in assembling the charges together to their respective locations by bringing them from infinity. So that means we are bringing the charges one by one to their respective locations, and what is the total amount of work done that is stored as their potential energy. Now take a simple system of 2 point charges Q1 and Q2 with position vectors R1 and R2 with respect to certain origin, and R12 represents the distance between the two charges. Now by definition we are bringing the charges one by one. Let us bring the charge Q1 from infinity to this point. Suppose this point is A and this point is B. To bring the charge Q1 from infinity to point A, the net work done will be 0 because there is no external electric field. No electric field is present before. We are bringing the charges one by one. When we are bringing the charge Q1 from infinity to point A, work done equal to 0, that is W1 equal to 0. Now let us bring the charge Q2 from infinity to point B. At point B, the charge which is present at A will produce an electric field. As now already an electric field is produced by the charge Q1, and we are bringing the charge Q2 inside that electric field, some work is done against the electric field due to Q1. Now the electric potential produced by Q1 at point B, that is given by V is equal to 1 by 4 pi epsilon naught Q1 Q2 by R1. Sorry. 1 by 4 pi epsilon naught Q1 by R12, because this is the potential due to a point charge. V is equal to 1 by 4 pi epsilon naught Q1 by R12. And you know what is electric potential? Electric potential is the amount of work done to bring a unit charge from infinity to that point. So now if you are bringing a unit charge from infinity to point B, then this is the work done. Then what is the work done when you are bringing the charge Q2 from infinity to point B? When you are bringing, listen carefully, when you are bringing unit charge, work done is this much. When you are bringing charge Q2 from infinity to point B against the electric field of Q1, what is the work done? That work done, suppose W2, that is equal to Q2 times this potential, Q2 into V, that is equal to 1 by 4 pi epsilon naught Q1 Q2 by R1. So now the total work done for this configuration to bring the two charges from infinity to their respective locations, that is W will be equal to W1 plus W2. So that is equal to 0 plus this one. So 1 by 4 pi epsilon naught Q1 Q2 by R12. This work done is stored as the potential energy of the system. As the electric field is a conservative field. So which path they are following to come to point A or to point B, it is independent. It does not depend upon the path which is followed to bring the charges from infinite to their respective locations, because electric field is a conservative field. Electrostatic force is a conservative force. So this is the expression for potential energy due to a system of 2-point charges in the absence of an electric field. Now let us take a system of 3-point charges Q1, Q2 and Q3. The distance between Q1 and Q3 represented by R13, Q1 and Q2 is R12, and the distance between Q2 and Q3 is R23. So as before, to find out the potential energy of the system of 3-point charges, we will bring the charges one by one. As before, for a system of 2-point charges, you have seen when you are bringing the charge Q1, let us start from Q1, then we will go for Q2, then Q3. When you are bringing the charge Q1 from infinity to point A, no work is done. So W1 equal to 0. Why? Because there is no electric field before. Now, when you are bringing the charge Q2 from infinity to point B, as already Q1 is present, so it will produce an electric field and we have to do work against that electric field. And already previously we have calculated the work done W2 is 1 by 4 pi epsilon Q1 Q2 by R12. Now next is to bring the charge Q3 to this point A, B, suppose this point is C. And now already Q1 is present at A, Q2 is present at B. So both will produce a potential at point C, which is given by 1 by 4 pi epsilon naught Q1 by R13, Q1 by R13 plus Q2 by R23. This is the potential which is produced by charge Q1 and Q2 at point C. This potential is the amount of work done to bring the unit charge from infinity to point C against the electric field of Q1 and Q2. Now when we are bringing charge Q3 from infinity to point C, what is the amount of work done? Per unit charge, work done is this much. When we are bringing charge Q3, work done is W3 equal to Q3 into that potential. So if you take the product, we are getting 1 by 4 pi epsilon naught Q1 Q3 by R13 plus Q2 Q3 by R23. Now, what is the total work done in assembling the charges to their respective locations? That is W1 plus W2 plus W3. On adding all these three terms, what you will get? W is equal to the potential energy of the system, that is 1 by 4 pi epsilon naught Q1 Q2 by R12 plus Q1 Q3 by R13 plus Q2 Q3 by R23. So now, as three charges are there, we are getting three terms. Previously for 2 point charges we have got only one term. Similarly, this result can be generalized for a system of n point charges. Now let us generalize the previous result for the system of n point charges. And for n point charges, we can write the result in the summation form 1 by 4 pi epsilon, that is common for all, Qi Qj divided by Rij for all pairs. How many pairs possible? All the pairs will be included. That can also be written in the splitted form half into 1 by 4 pi epsilon naught summation I from 1 to n summation j from 1 to n Qi Qj by Rij, where I not equal to j. That means Q1 Q1, that pair is not possible. So if we are considering all the pairs, the summation for I and j both, then every term will appear twice. That means suppose I1 j2, the j2 I1, both are same. So the terms are, the pairs are repeated when you are taking the summation over I and j both. That's why the term half is included here. So this is the expression for the potential energy for a system of n point charges. U is equal to half into 1 by 4 pi epsilon naught I from 1 to n, j also from 1 to n, I not equal to j, qi qj by rij. Now let us solve a question based on the electrostatic potential energy. Now there is a system of 4 point charges plus q, minus q, plus q and minus q located at the vertices of a square of side, suppose R. And the question given, what is the total work done to bring the charges to their respective locations, or to make this configuration, what is the total work done? You know by definition the total work done to assemble the charges to their respective locations is the potential energy of the system, and it is a system of 4 point charges. Suppose this is q1, this is q2, this is q3 and this is q4. For a system of 4 point charges, how many terms will be there? Let me write. So u is equal to 1 by 4 pi epsilon naught q1 q2 by r, all the distances are r, plus q1, this distance is r, this is r, this is r, so diagonal will be root 2r, this diagonal also root 2r. So q1 q2 by this distance is r, then q1 q3 by root 2r plus q1 q4, once again this is r, plus q2 q3, this is q2, this is q3, so divided by r, plus q2 q4 divided by, this is q, this is q4, so root 2r, plus q3 q4 divided by q3 q4, this is divided by r. So like this 6 terms possible. Now we can take common 1 by 4 pi epsilon naught r, r is common to all. Now let us put the values. q1 is plus q, q2 is minus q. So q minus q, this is minus q square plus q1 q3, this is plus q, this is plus q, so q square by root 2 plus q1 q4 plus q minus q, so it is minus q square, r already have taken common, divided by r, plus q2 q3 minus q plus q, so it will be minus q square plus q2 q4 minus q, that is plus q square, and this will be once again root 2 plus q3 q4 minus q plus q, that is minus q square. So all total, how many terms you have got? Minus q square, minus q square, minus q square, minus q square. So all total 4q square, everywhere q square is there, so I can bring q square outside, so q square by 4 pi epsilon naught r, so inside bracket, so minus 4, because it is minus 4q square, and 1 by root 2 plus 1 by root 2, so 2 by root 2, that is nothing but root 2. So this is the potential energy of the system of these 4 point charges, and this is also the work done in assembling this configuration or assembling the charges to their respective locations. In the next bit of this question it is given, what is the work done if I bring another charge q0, suppose another charge q0 is brought from infinity to this point when these 4 charges are present there. And now it is a system of 4 point charges. When you are bringing a unit charge to this point, that is nothing but the electric potential at that point. The electric potential at this point is is the amount of work done to bring the unit charge. Then what is the total work done to bring the charge Q0 to point E? So that work done W is equal to Q0 into V. Then Q0 into what is V here? V is 1 by 4 pi epsilon naught, and you know all these distances are same because it is the half of the diagonal of the square. So this is root 2 and this is root 2 r by 2, this is root 2 r by 2, this is also root 2 r by 2, this is also root 2 r by 2. All the distances are same, and if you add all the charges, you will get a 0. That means total work done to bring the charge Q0 to point E will be 0. Similarly, another point may be here given. Suppose it is given what is the amount of work done to bring the charge Q0 from infinity to suppose the midpoint of this line. So what you will do? At the midpoint of this line you will find the potential. For that you have to join this one, you have to join this one, then find the potential at this point and multiply the charge Q naught to get the amount of work done to bring the charge Q naught from infinity to this point. So this way you can solve the numericals. These are the simple type of numericals. Those are coming in your board exam.